All right, good morning. Today we're going to talk about control charting and the control charting exercise. Um, and I've done screenshots of some of y'all's spreadsheets, and so I can give you tips on how to rearrange them and everything. And so anyway, we'll talk about your particular data. So far, I just gave everybody full credit on all of those because we haven't had this lecture about how to format the data. So I figured I'd let you go for a while, and then I'll give you tips. And so then starting after next Saturday, I'll start taking off if you don't do what I say, right? so I figure that's fair, right? So now you've got to see how I want the data and everything, and then you'll be held accountable for doing that. So there's some folks that need to make some changes. It's not a big deal. You just copy and paste and move things around. So it wasn't any real big problems. And so let's think about what control charting does for us. And so this is this idea of this process control variable. Now you can't, but actually I think it's a safe statement. You can't collect every piece of data that you want to. I mean, and you spend all your time trying to collect a whole bunch of things when there may just be one value that really is the important value. So you've got to try to find what that key process variable is, and that takes some thinking, right? So at Pantex, where I worked before, they were trying to control every little thing, and so they had some control variables that they were measuring, and one of them was their balances. And so they would come in the morning before they started work for the day, and they would put a little check mass on the balance. And if it was like a 1 gram weight, and if that measured plus or minus 0.0002, they said the balance was out of calibration. And so then they would red tag the balance. And then they couldn't use that balance until the metrology group. Metrology is sort of the measurement of your measurement devices. So they would come over there and they would put the little masses on the balance, and they would see if it's measuring accurately, and they would calibrate the balance if it needed calibration, and they would take the red tag off. So that's sort of the basis of their whole analytical lab, was based on controlling that balance. So it was a key process variable. What they were trying to do, though, is they were trying to control it to essentially the number on the box. Like when you buy the balance, it says accuracy to plus or minus 0.0002 grams. Then that's just like one standard deviation. That's the standard deviation of a single measurement, and they were trying to control it to one standard deviation of variability, and that was too tight. And so, what do you remember? Do you remember from our lecture what the confidence interval is, plus or minus one standard deviation? So, what is 95% confidence? How many standard deviations is that? 1.96. So almost 2. So plus or minus 2 standard deviations is a little bit better than 95% confidence. You're covering a little more, like 4% more of the distribution of natural variation by using 2 standard deviations. What is plus or minus 1? 68 or something. Yeah. So what is 1 minus 68? 32. Okay. So 32% of the time, this balance is going to be out of calibration. So just 10 days, that's going to be 3 days out of 10. So in a two weeks of work, they're going to come in on that balance, and when the balance is acting perfectly, they're going to have 3 days out of 10 that they're shut down. Now for the technician, that's great. They red tag the balance and they go sit in the break room until metrology comes over. And so they're getting out of 4 hours, maybe a whole work day of no work, just because the balance was behaving like it should. The metrology kept saying, you guys got to quit calling us over there. There's nothing wrong with this balance. So that was just a bad policy. They wrote the policy poorly to control it to what plus or minus 1 standard deviation. When 3 days out of 10, it's going to be outside that limit with no special effect. Like a special effect is something that's non-random or a special cause. So with no special causes, that balance is going to be out of spec 3 out of 10 days, and that's a problem. So that's more like setting your specification limits, but that balance would be what we call a key process variable. If everything you do in that lab is based on that balance, then that would be something that you could do. But it's sort of at the beginning of the process. Maybe you want to pick a check sample. Let's say you're doing GCMS and you want to weigh your sample out, you want to do your dilutions, you want to put a check sample in to measure your calibration curve, and then you run it on the GC and see that it comes out at the right retention time. So notice how that captures more of your process. That captures your dilutions, your pipettes, your balance, and all of those things. So maybe that's the one thing that you want to control chart. So finding the variable that gives you an indication if something's wrong in your process, that's what we're talking about. Now for you guys, I'll just let you pick a variable like the temperature or a stock or something like that, mainly so you can get practice with the control charting. Okay, so this variable indicates the performance of the equipment and the process, ideally. And if the process is unchanging, the variable should be unchanging. Okay, so that's the real important point. Like this should have a slope of 0 over time. It should bounce all around, but the slope should be 0. And so, it should only change when there's random fluctuations. And if it does change, like more than 2 sigma, then there's only, if it goes high above 2 sigma, then there's like less than a 2.5% chance that it would have gone that high. If it's way past sigma, then it's like a 1 chance in a million. You've got a really big event that has happened that's non-random. Okay. So like you're doing water intake, right? It's probably going to jump around quite a bit. Mm-hmm. And so you're going to eventually see there's a trend, pretty wide error bars, but let's say you get sick and you just sleep all day. That whole day is going to be low because there was a special cause. It wasn't just random fluctuations. You were sick, you didn't drink water. Okay. So this should, even though you kind of know, hey, something happened, if you didn't know, the lack of water that day would have indicated something special happened that day, something non-random. And so that's what we're looking for. When we say that there was an event, something non-random happened that day, if you go out of those control limits. We've gone through the control chart. You should all have your approved data and be collecting it. I've seen it's great. You're close to 15 data points. Some people are past 15 data points. Remember to do the differences correctly. So today minus yesterday, I will get in there and check that and start taking off points if that's backwards. Okay. And then once we finish the 15 days, we should compute the mean and the standard deviation using the Excel formulas, average and standard deviation. Since we're doing 15 days, let's use the population standard deviation. Okay. And so, if you're measuring the daily temperature, daily changes, or pressure, or pollen, etc., there's this random fluctuation. And what we're looking for is when it jumps more than 2 sigma from that normal behavior, something significant has happened to the process. And that was the problem with those balances at Pentex. Nothing significant was happening. The other thing that was a problem with that process is they were not ever really measuring things down to that small. Like I asked them, what's the smallest mass you ever measured? And they said probably 0.01, something 0.01 and then whatever decimals we have. And I said, so you're really worried about that 100th place. Why are you trying to control it to the 4th decimal place, the 10,000th place? When that's going to be your 3rd significant figure, and your uncertainty, if you wanted 2 significant figures, would be in the 3rd decimal place. You're trying to control it to the 4th decimal place. So what you really need to do is write your spec. If it's ever greater than, say, 3 sigma down in the 4th place, which would get it up to 6, or you could even say 0.0001, then it's really a special cause. Like if you put a 1 gram mass and it measures 1.001, then that's significantly different than 1. And it's getting close to the decimal places which you consider significant for your process. So set your limits wide, and if something really bad happens, then you'll know it. And if nothing really bad has happened, then it's in the noise, and so you wouldn't care. Now, what is this philosophy behind control charting? It's a thing called Kanban. It's using these Japanese figures here, okay, and it's a part of a process, a Japanese word called Kaizen, and it's Kaizen is the philosophy of continuous improvement, and so you can always improve a process. That's what Kaizen stands for, and a Kanban is like a sign or a flag. Like if you come in and you see a flag, your eye is immediately drawn to it. Nothing else in the room has changed, but there's a flag over there. What's that? And so that's what the Kanban is. So can I get you to close it? Yeah. So if you're working if your process is going fine, there's no flags. But if you run your check sample and it's outside of 2 sigma of the normal mean, then that's a flag. That's when you take action. So think about this. If you were doing calibration checks in industry, and you can use a push philosophy or a pull philosophy. So a push philosophy is like a calibration schedule. Let's say we're doing GCMS and we have on our schedule, before we run any runs that day, we're going to recalibrate the instrument. So every morning you come in and you recalibrate the instrument. Sounds like a reasonable thing to do, right? Because you're going to run samples that day. Let's recalibrate the instrument and let's run the samples. But is your calibration always perfect? Probably not. Has the instrument substantially changed from yesterday? Probably not. So you're spending a lot of extra time and you're not making the situation better. What if you had a really good calibration on Monday and then Tuesday, your hand was shaky, you weren't feeling as good, you did a poor calibration, you've actually made the situation worse on Tuesday when you didn't need to. So with you constantly fiddling with the knobs, you're actually introducing uncertainty into the system. The more times you fiddle with the instrument, the more times you're injecting your ability into the instrument. So that would be a push. You see, you're pushed into doing something. You calibrate every day. So I'm pushing you to calibrate every day, and I'm pushing you to fiddle with the instrument and actually introduce more uncertainty. It's going to reduce your precision over time because you have a different calibration every day. Okay? So samples you ran on Monday may be different than on Tuesday and may be different on Wednesday because you've got different calibrations, and you're introducing that uncertainty yourself. So it also increased costs because we're paying you to do those every day, and that's not billable time. That's not time that someone else is paying you to do. We're paying you to do that, and that costs money. Okay, and it costs. You can also miss problems that happen between this schedule, because let's say you calibrate in the morning, and then that afternoon, I don't know, something happens. A cold front comes in, and the air system switches from air conditioning to heating. And now the whole room jumps 5 degrees because there's typically a window. You cool down to say 72, but you heat up to 68. Now the whole room has changed 4 degrees. What does that do to your flow rates and so on? So something substantial could have happened between calibrations and you didn't catch it. Okay. Now that might be more susceptible if you say calibrate on a weekly schedule. We're going to calibrate on Monday and use that calibration all week. And then something happened on Wednesday and you didn't recalibrate till the next Monday. And so all of those samples, Wednesday, Thursday, Friday, may have had a problem and you didn't catch it. So that's what I mean by you may miss things that happen between scheduled calibrations. So control charts work on a pull philosophy. You only act when you're pulled into the behavior. You see the difference in a push. A schedule on the calendar, which has no connection to the data, is push. I'm pushing you into action. Whereas a pull philosophy is, I look at the data, I track my key process variable, and all of a sudden I see a problem, and now I take action. So that's the Kanban, that's the flag. So I run a check sample, maybe I run a check sample every 2 hours. So I'm running on a calibration, run a check sample, it's still good. That's a key process variable, and I'm control charting it. And then I go along another 2 hours, I run another check sample, it's still within that acceptable range, I'm still good. Day after day after day, I keep running my check sample, and it's all still good. And then Tuesday afternoon, it's out of control. That's my flag. I'm pulled into action now. And it pulls me forward, and I start, maybe I run another one. There's like a flow diagram. I run a second one, it's out. So I've got two that are out now. We're going to take action, and we're going to recalibrate the whole instrument. So we pause work, we do a new calibration curve, run our check sample, it's back in the envelope, and we're able to work again. So we see how we're pulled into action. It's not on a set schedule. They say, when do you calibrate? Monday, Tuesday, what? No, we don't calibrate on the schedule. We calibrate when the instrument goes out of control. And that seems weird, but what if your if your instrument's good, you might be operating a whole month on one calibration. How can you be confident in that? Your key process variable. You keep running that check sample, it keeps showing up in the envelope. And so you're still good. So that can save over time an enormous amount of cost, of time. Time and cost are essentially the same thing. And it can actually lead to, over time, better data because you're not introducing your own uncertainties by unnecessarily calibrating all of the time. And so we'll calibrate only when the system tells us it's needed. That's the pull. So the system tells us. So we're pulled into action. And so that's what you're seeing with your data. You're going to be collecting your data. It's going to be random variation. And then all of a sudden, bing, it's high or it's low. And that's when you're pulled into action. Now, your action is really easy. You just kind of explore what might have caused the data to go out of control. If you're doing a stock, like Apple stock or whatever, you go on to Google Finance and look up that day and see if there's an announcement as to why the stock went high or the stock went low. Okay, and you put your little URL link in the table, and you put your little, it's just a couple of sentences. That's all I'm looking for, and a link to where you found your information. If it's personal information, you don't have to have a link, right? But you can just say, yeah, I was sick that day and didn't drink as much water, whatever it is. Or my dog was playing fetch and he had a lot of energy that day, so it went long. And so anyway. And so this improves quality because, again, our performance is frequently monitored and we're not introducing ourselves into the process as much. So in Minitab, you can do control charts in Minitab. So if you have your data like this, you do the stat, control charts, variable charts for individuals, dot, dot, dot. The dot, dot, dot means you're going to get a dialog box. And so you punch that. And so we got a volume. You can come in and do labels and pick the data for your labels and select various options. You can pick this scale, hit that scale and do a timestamp and then pick the date column. So that'll timestamp your X values. Then you hit I options and come up here and you can set the mean and the standard deviation. Where do you get those numbers? Okay, you got to calculate them. Okay, so you calculate that mean for the first 15 values and the standard deviation for those first 15 values, and you enter them in there. Okay, and then under more options, you have this. You want to do display the control limits. This has 0.632 multiples of the standard deviation. I do 2 plus or minus 2. This was just the defaults for some reason. And then this is the other option on these tabs. So up here, this tab across the top, this tests. And so these are tests for being in control. And so you can set different tests based upon your process, what you're trying to monitor. Let's say you really don't care if it goes low. You're just really worried if it goes long or high, right? And so then you can just set it if it goes above or what have you. Maybe you're worried about drift. And so you want to look for a certain number of data points on one side of the mean, because that means it's drifting. So let's look at some of these tests a little closer. And so this is in units of standard deviation. So you can see over here, they're saying if we have 1 point, that's K standard deviations from the center line. So the center line is the mean. And so this is saying if we have one data point that is 1 standard deviation above the center line, then this is going to flag that and say you're out of control. Now that's a little too tight. That's plus or minus 1 standard deviation. But you have the option to change that. You could change this to 2 Okay, you can change it to 3 and so on. In our process, it's going to be 2. You could do 1.96 if you wanted exactly the 95% confidence interval, then you would say 1.96. Now, K points in a row on the same side of the center line. What do you think that would test for? R squared?
Well, there's R squared.
Think about if it's going high or going low. Like if it's drifting high, then you would have X number of points above the center line. Now there's gonna be, it's gonna be random. It's not always gonna alternate, right? And so you might have 3 points or so on. But what are the chances of it being on one side or the other? Like if it's 50-50, right? So what's the chances of having 2 on one side? Yeah, 0.5 times 0.5 or 0.25, okay? And then 0.125 and then 0.0635. So the probability of being on one side of the mean is 1/2 to the number of data points power, okay? So 0.5 to the n. And so if n equals 5, or we could use k, if k equals 5, then it's 1/2 to the 5th power. So it'd be really, really small probability of having 5 data points on one side of the mean. And so you could do that, and this is a situation where they say 9. So the probability of that happening randomly is 1/2 to the 9th power. So if you get 9 points on one side of the mean, your data may be drifting. And so this is the test you would pick for drifting data. You don't want to pick all of these because you're going to be running to the lab all the time because your flags keep going up. You're like, I got to recalibrate. So you're trying to tamp it down too tightly, and so you want to pick the ones that are strategic for your process. If you know what that would be. Here's K points in a row, all increasing or all decreasing. So notice how that's different than just being on one side of the mean. This is a real drift. It's this point, and then the next one's higher, the next one's higher. And this one can be, starting negative and creeping up to positive or vice versa. It's not even picking the sign of the point. It's just, was this point larger than the last one? And the next one larger than that one? And the next one larger than that one? And so this would be 6 points, all increasing. Okay, what about alternating up and down? Again, that's not random either. How many times would you need that? Well, this is, that you're going to have a lot of that behavior, but this would be 14. If that happens 14 times, 14 data points, up, down, on the other side of the mean, then it says, okay, you might have a problem you want to look at. Okay, so this is K out of K plus 1. So 2 out of 3 points greater than 2 standard deviations from the center line. So this is a little bit harder than this one up here. So this one might be too easy. So this is a little more difficult. This is saying, okay, if I'm only going to take action if 2 out of 3 of my data points are 2 sigma away. Okay. Or you could do that with 4 out of 5 points are 1 standard deviation away. So none of them are 2 standard deviations away, but 4 out of 5 are 1 standard deviation away. And so we had a 32% chance of it being 1. So this would be on one side or the other would be 16% chance. So this would be 0.16 to the 4th power. So again, a small probability that you would have that. And so then 15 points in a row within 1 standard deviation. Now, what is that one about? You want things to be in control. You want them in that envelope. But this is saying 15 points in a row inside plus or minus 1 standard deviation. Why is that a problem? Yeah, what does that suggest to you, perhaps? It's a little strange test, and I don't know why this would concern you, except that you want to know your system. Okay, so you've got an uncertainty, and then all of a sudden it tightens up for 15 data points. So that's telling you your system has changed. It's not drifting. It's not becoming more variable. It's becoming less variable. But that's also not random. So it's detecting if there's a change in your standard deviation. And it's a whole new population. It's 15 data points. So if you have 15 data points and they're all tighter now, then something has changed that's not random. So your standard deviation has changed. So maybe you want to take those 15, recalculate the standard deviation, and start plotting the control chart with that new one. Because that's how it's been behaving for 15 data points. You've got a new standard deviation. So anyway, it's just a lot of different kinds of statistical tests that you could use to see if your process is in control. The last one, let's see, 8 points in a row, all greater than 1 standard deviation from the line. So this is just saying that nothing's outside your action limits, but they are outside your watch limits for eight measurements. And so once again, your standard deviation may have gotten worse, but it's not so much to throw it out of the plus or minus 2 sigma. And so maybe you want to check into it. Okay, this one also would catch like this one that's 15 inside. This one here might catch some funny business. What do I mean by that? Somebody's dry labbing it. They know the mean is a certain amount, and they're not actually running the check sample. And they're just writing down the numbers. And they know if they write the same number down, they pick the mean, and they just write down the mean, they're going to get caught. And so they just start fiddling with the numbers and adding 0.15 or subtracting 0.9 or whatever, and they're dry labbing it. And you would catch them with this because they're probably not going to have a statistical variability that matches the uncertainty of the instrument that you actually measured. Okay, so some of these can catch, again, that's not a random variation. That's a person messing with the data, and you might be able to detect that here too. We wouldn't expect that in a crime lab, but stranger things have happened. So here's a picture of the control chart that Minitab produces, and it shows these little indicators right here. So these points are red, and they have little numbers by them. And so that's nice because those numbers then are explained in that session log. Remember I said Minitab has the data that it produces, the charts that it produces, and then a session log that has everything that you've done in the session. And so if we go to the session log, we'll see what those numbers are. All right, so let's look at those. So here's the test results from that control chart, and it said test number 1, it failed at 0.17 and 18, and we had 1 point more than 1 standard deviation from the center line. Okay, and then here was test number 7, 15 points within 1 standard deviation of the center line. I said invalid warning. It may be invalid for most processes. It's just saying your standard deviation may not be accurate. And so that one failed at points 15 and 16. And so anyway, and then it says if the graph is updated with new data, the results above may no longer be correct. So it's just giving you that warning that this was for that graph run on that particular day at that particular time. So here's the control charts that you're going to produce in Excel. It'll look just like this. The only thing I might correct if I saw this is I would say that your date is colliding with your categories. And so I would say move this over a little bit so it doesn't collide, so that I can tell that that's 3, that's April or March. And so don't have your dates colliding with your category label here. Also, look how the dates are formatted. They're 90 degrees. I want you to learn how to do that, so I'm requiring you to do that. Look at the date format. It's month, day, year. Okay, but the slashes, don't have it spell out like 30 Jan or whatever. Go ahead and do it this way with the month, day, year. You can set it up to where these are Mondays. If your first data point is on a Monday, I think so, yeah. And so Monday, and then you skip 7. Now you may only have 5 days of data, but you're still putting that category access in and you're skipping 7 categories, and so then you'll see that and and check that to make sure that that's right. Sometimes I'll say skip 7 or 5 if it makes you do that. I have to go back and check to see. But the point is, have it be every Monday. So it's showing me every Monday here. And so I see each week. I can look at that and see what each week it is. And so on. And so then we look at the data. Like let's just pick this week. So that's Monday, Tuesday, Wednesday, Thursday, and Friday. And then it is hard to see, but there are skipping 2 spots there. And then this is Monday. And so this is daily change. And so for Monday, I'm just subtracting Friday's value. I'm not putting zeros in for Saturday and Sunday. Because if you put a data point in the table like a 0, then you're saying you measured that. And so don't ever just enter zeros. Okay. Just forget about Saturday and Sunday. Just subtract Friday from Monday and move on. Okay, so then the actions, I didn't want to get in there and really do the sigma in my labels, and so I'm not making you do that either. But so I just used S, but in reality, these are sigmas. If you want to do that or try to figure that out and putting the sigmas in the legend, I don't know how to do sigmas in the legend, but maybe you can figure it out. Okay, so if you figure it out, I'll be thrilled. Okay, but anyway, this is the watch, which is plus 1 sigma, and this is plus 2 sigma. It's really the mean plus 1 and the mean plus 2. You see, here's the mean, and then this gap here is mu plus S, or sigma. And then this is, up to this point, mu plus 2 sigma. And those are your high limits. And then your low limits is the mean minus sigma right here. And then this limit here is mu minus 2 sigma. We take action after it goes 2 sigma out. And so that's what these arrows are pointing at. Those are the out of control points. And in this case, we have one that's outside of the control point with the initial training period. Also, I have the training period done in green. Green for the training period, and then the rest of the data is black. Now, how to do that easily in Excel? Go ahead and plot all of the data, or you can plot the data from this point forward in black, and then have a separate series plotted of the training data, and just make the colors different for that series. So you really have 2 series on here. You have the trainings data series, and then the control period series. Makes sense? And then this is markers with connected lines. Not smooth. Okay. So do not use the smooth lines. It puts all this little craziness on there. And again, you don't know the equation of that line, so don't use it. And then these lines are no markers. And then you can double click the line or click it once and do format selection, and you can get in there and change the color to red and change the color to yellow for the watch and green for the mean and so on. Now, I don't really care, but you can see how the data goes on top of these lines. You can have it on top or behind, but you can control the order of the legend, the order of the data. Using in Excel, if you click on a data series, you can see in the little formula bar, you can see the title of the data and a comma, and the X values for the data and a comma, the Y values for the data and a comma, and that last number is the layer number. Like whether it's the first layer or the last layer. You know, if there's 1, 2, 3, 4, 5, 6, 7 different things plotted on this graph, and so they'll go from 1 to 7. And all you got to do is just select that 1 and type in a 7 and hit enter, and it'll move it to the 7th slot and slide everything down. So you can control your data series, which one's on top of the other, by playing around with that order number. And that will also rearrange things in your legend. So let's say, it's all mixed up and the means at the top and the actions are next and the watches are next, and you want to get them all in order like this. Just click on each data line. Like if I'm going to click this line and I want to make it slot number 3, okay, I click that line, go up to the bar at the top and find that last number in the parentheses, select it and type in 3 and hit enter, and then that one will move to 3 in the legend. Okay, so that's how you can control the order of those things. This is all on video too, so if you can't remember that, just go find it and see if you can make sense of that. Okay. And so whenever we go beyond the limits, we must take an action, and an action is making a log entry. Okay, this is data reporting tips from your actual data. So this is snapshots of student data, and so I like this here. So kudos to this person for putting a little description of the data in there. So everybody put a little description of the data up at the top, maybe even like a link or something. I don't know. It's kind of nice. But anyway, this is nice because if someone else then looks at the spreadsheet, they know what's being plotted. So let's go ahead and do that. So just push all your data down a couple of lines and put what you're collecting and where you're getting the information. Okay. Then I like this too, although I like this date format better over here. So let's go with this date format instead of this one, because this at least has the year in it. Okay. And then that's likely going to be then the date format for the chart. And so let's use this date format here. This is nice. I like this up here. It's got the date format. It got some use of color here. There's a little comment. That's nice. This is really just a data comment, and so we're not really controlling our action log. We're going to have a thing called an action log, and I'll show you that in a second. Okay, and so this is really just a data log, data comments. How about that? Okay, and this is also good. I like this these comments. The thing I would change though about this is I would move the comments here. I would move those to the right, and I would move this over here to get it actually next to the date, because that's going to make it easier when you go to plot. So you can select 2 columns. The first column is your categories. The second column is your data, and you do a line chart, not an XY scatter. Is everybody clear with that? It's a line chart that you're going to do. And the x-axis is called the categories. So it could be anything. Ours is date, but it could be anything. A line chart could be like a count, like in the cafeteria, how many apples, bananas, and desserts they have, right? It's a category of apple and a number, category banana and a number. So the categories can be text, can be dates. If they're data, then you have an XY scatter plot like we had in PChem. If it's a calibration chart, you have XY scatter. You have X is the concentrations, Y is your signal. It's 2 data points, numbers. But in a line chart, they're not numbers, and dates aren't numbers. Dates are categories. So whatever happened on this day or that day or that day, those are categories. Here's some other formatting tips. This one here is a problem because the unit is in the cell. And so this is not going to be numbers. See up here, this is the cell. And so you got text and numbers mixed. So numbers and text. So don't mix. I'm writing backwards, just like Yoda. Don't mix these 2 in one cell. Does it make sense? So you move, or you just put the unit in the title. And so you might say time/minutes, and then just put the numbers. So then you can plot the numbers. Okay. And then it's also very clean. And also this right here, this is text as well. So you don't have to type in, and I know it's text because Excel would not capitalize Friday, but not capitalize Thursday, right? So I know it's not automatic. That's what I clued in on. And then you click on it too, and you can see it's typed out here. So go ahead and just, for January 19th, type 1/19, 2023, and Excel will see that, and it will make it a date. It will say, I recognize that's a date, and so it'll make it a date format. Now, sometimes Excel does, where is it? I saw somewhere, there's a lot of date formats in Excel, and sometimes it will say Friday, January 19th, 2023, and it's using a date code and producing all of that text. But when you plot it, it's going to have all of that information in there. So that's why we don't want it to say Friday. That's going to take up most of the page, and then your data is going to be at the top in your chart. Your categories are going to be so long that your data is not going to be very well plotted. And so this is the best date format to use because it's the most it takes up the least amount of space. So okay, and then let's look at this one. Okay, so this is skipping the weekends, and so in this case, this is a problematic case because we're doing daily difference, but on the weekend a 0 was entered. And so look at the daily difference. It's -97. And then on Sunday, a 0 was entered. Of course, Saturday and Sunday, that gives you a 0. And then on Monday, the difference gives you a +97. And all the other, look how small the other differences are. Okay. And so the chart's going along like this, and then it has this thing like that, which is the weekend. A positive and a negative difference. And that's going to screw up the data. You're never going to see the fluctuations here because you have this thing right there. And so if you just ignore the weekends and you take, Monday minus Friday, then it stays in control. And don't ever enter 0 when you didn't actually measure a 0. So that's, yes.
You have to skip the weekend, or is this just if you do?
Like stocks are not reported on the weekends, and so they have to. It's up to you if you're collecting like personal data or whatever. You can take the weekends off if you want and just report Monday through Friday, but just take the Friday and subtract it from Monday. So Monday minus Friday is totally fine. Yeah, so we can do that. Bless you. And then in this case, don't even put them in the table. And so you can just come over here and you can just delete these 2 rows. And just have Monday through Friday, Monday through Friday, Monday through Friday. Okay. And then just, it's easy with the formulas then. If it's adjacent minus the one above it, and you just go all the way down, and since Monday is right below Friday, it'll do the correct subtraction, and it'll just go all the way down. You don't have to worry about then, because then if you do it this way, then this formula is different than all of these other formulas because it's going over minus up 3 cells, and all the others are over minus the 1 cell above it. So make life easy for yourself and just not even include those rows if you're not going to collect data on those things. Okay. And then tables should be vertical. So this one and these 2 both are collecting data horizontally. So see the dates going across? And this one also, dates going across. That's going to be, you can force that to work, okay? You could take this horizontal series and plot that, but it's just not convenient. The table goes way off, and you can visualize the tables better if they're vertical, and you can do your formulas a lot easier and so on. So just change these. There's a fast way to do this. If you want to take this and you select this table, select the whole thing, copy, so select and Control C. Okay, and then you come over here, pick a cell right here, and do edit, paste special. Dot, dot, dot. So it gives you a dialog box. And then you go in there and you say transpose. So you click the little checkbox that says transpose. Do you remember from PCHEM? Transpose takes a vertical to a horizontal or horizontal to vertical. And it'll flip that table to vertical and paste it down, and all your data is right there. Okay. Now, if you've got formulas in there, you may have to go and fix the formulas, but the data, at least the dates and the data, will be dropped in a vertical format. So that's a fast way to do that. So you're not having to retype everything. It's not just about tediousness, right? If I'm retyping everything, that's really tedious. It takes you way longer than it needs to. It's also prone to mistakes. The more little typing and reading and typing that you do, the more you're going to transpose numbers. And that's another thing that people have studied. Like, how many numbers how many numbers can you type before you transpose 2 of them, right? And so it's like the mean time between failures. And we're fallen creatures. I mean, we can't do it perfectly. So I've sort of ruined my ability to remember numbers because I'm always worried about transposing numbers. So I have to like visually read the numbers out and type them in one at a time. I don't put them in my memory and then type them from memory. So all these freaking authentication codes that I get are a real nightmare for me because I have to actually see it and then go and type it in because I just can't remember numbers. You tell me a phone number, forget about it. I got to type it in right then, and it's really bad. I'm glad that I didn't ruin myself earlier, or I would have had a real hard time with my locker combination as a kid. Yeah. Right. I mean, I guess if I really work on it, I can remember numbers, but I've pretty much ruined my number short-term memory because I don't trust myself. I'm going to see it when I type it in, and that's a problem. Okay, once you have all your data sort of put together, this is the way we're going to set up our spreadsheet. So nice vertical table. You got some information up here about what you're collecting. Go ahead and give yourself a few more rows, like scoot it down some more and do the measured mean. So the average of the first 15 days only. So only the training period. And then the same for the standard deviation. So we're using that population standard deviation. I think in your notes, if you can dig in there and see, it says .s, but that's a mistake. We'll do standard .p. Again, only the first 15. Because that's the training period. That's when we learned about the standard deviation of our process. And we're going to keep that the same to see. So it's like curbs on the street. It took a while to find them, but then we pave those curbs. And then we see if our process stays inside the curbs. We don't want the curbs moving all of the time. So it's not a running average. It's not a running standard deviation. It's a fixed curve. And so once that's fixed, and then we can go on and make our curbs. These are the curbs. These are our watch and action limits. And so I've just shown the formula here, right? So this is the mean minus 2 times sigma. So I'm just referring to those cells up there. And notice how they're anchored. So it's the same formula all the way down. Now, there might be a more elegant way to produce these lines, but this one works, okay? And so every date has a watch limit plus minus, an action limit plus minus data point on it, but it's the same data point. And so when I just plot those lines, they're straight lines across. I don't show the markers because there's a marker at every one, and it makes a really thick line, and it's really ugly. So I just do lines only, no markers. But you see how they're the same number all the way down for the rest of the semester. And those are your curves. And so then I plot this whole thing from the date all the way over. I select all of this all the way down. And, well, actually, I plot the training period, and then I select everything from here down and plot that as the next group. Now, this is convenient to set up some alerts, and so on. You can have an alert column. So this is D, H, and I. And so this formula is kind of hard to see, so I'll blow it up. This is using the Boolean functions, if then statement, and then an or function. So I'm just showing you this because it's nice. And say if, and then the or function. So this returns true if either condition is true. Okay. So if D8 is greater than H8, so H8 is my greater than, it's my upper watch limit. So if D is greater than my upper watch limit, or if D is less than my lower watch limit, then I'm out of control. And so then you have the condition. If this condition is true, then do this next piece. And then this comma means or else. If it's true, do this. Otherwise, do that. And this just means do nothing. So this is 2 commas or 2 quotes, nothing in between. And so this is sort of the quote part. It's doing nothing on this one. But on this one, it was beyond the action level. And so it was true. So it typed in beyond action level right there. And so I copy this formula down. If you don't have any data points that are outside your action levels, then you won't get anything. You'll think nothing worked. You click on any one of those cells and you'll see the formula. So the formula's there, and it's giving you the little double quote with nothing there. Or this may be even better. This is a nested if-then statement. So let's think about it. Let's say if D8, so if, open parenthesis, the criterion, if D8 is greater than H8, then that's above my action level. So if this is true, comma, type in the cell above action level, in quotes. That'll type that text in there. Otherwise, let's test if it's low. So we put in another if-then statement inside the first one. Otherwise, do this if-then statement. So if D8 is less than the lower comma, then type in below action level. Otherwise, do nothing, and you got to close both parentheses. That's better, actually, because it's telling you when you're above or when you're below. And so practice doing that with the if-then statements. I'd say do the second one. Get really familiar with these if-then statements because they're super easy. Like when I download your gradebook from Blackboard, and I've got my gradebook on Excel, so I download Blackboard's gradebook. I always grab the email addresses. That's a column in Blackboard, and I paste it into my gradebook on my computer. And I say, does this email address on this row match the email address on that row? If yes, we're good. If no, then like no, exclamation point, and that tells me if somebody dropped and my Blackboard gradebook has shrunk and the one on my computer still has the person that dropped, everybody past that person would get the wrong grade because Blackboard shrunk and my one on my computer hasn't. If I pasted those grades on Blackboard, they would all be wrong, or at least everybody from that person that dropped down would be wrong. And so I have an if-then statement to say, is the order still good? So this is really useful, and it's real simple. I hit paste, I look, okay, no flags, then I can paste my grades back and forth from Blackboard to my computer. So you can use these if-then statements in a variety of ways. In I would say learn to use them because they really are helpful. So this is a good way to do it. Now this is what I'm talking about with the alert log. You can have comments on your data. Like if you're again collecting personal data, it's good to kind of keep comments on there in case one of those points is out of control. But you don't have to report that. You only really have to report an action log. So when the data goes out of control, then you need to make an entry in your alert log. So notice there are only 3 entries because there's only 3 data points that are out of control. And so this person was collecting, it looks like daily difference in temperature. And so this one triggered, it was below the action level. It said a cold front came through, and go ahead and put the URL of where you got the information. So like if you go and do your research for that, just go up and grab the URL and paste that into the table so that I can see you actually looked and didn't just make something up. Okay. Now, I don't know what this is about. Maintenance was being performed in the building or whatever. You know, maybe the temperature, maybe it was temperature indoors. I don't know. But anyway, the point is, comment on probable cause. If you found it online, give me a URL. Okay. Any questions about that? Sometimes people's data just doesn't go out of control very much. And so they get to the midterm quality report, they have the control chart, but there's nothing out of control. And so that's fine. You can just say in the action log section, say this is the section where the action log would be included, but none of the points were out of control. Don't just leave it off. Address it. It's a requirement of the report. And so you say in the action log section, say this is where the action log would go, but there were no points out of control, so the action log is not included. So, that way I know that you know that there should have been an action log, but there didn't need to be one. So always address those things. So anyway, this is, again, your chart should be formatted just like this. This is a bad control chart. And again, what's bad about it? I think I've shown this one before. Yeah, that's right. So this is really not continuously variable data. So there's not 100 divisions or 10 divisions between the maximum and the min. There's only 4. So this is really what we call category data. So there'd be one answer, like 1, 2, 3, and 4. You see there are only 4 answers. It's kind of like a strongly agree, strongly disagree, neutral, whatever. It's not continuously variable data. It's like choices, like 5 choices, and you pick one of those 5 choices. The requirements to get statistics out of this kind of data are enormous because you have to prove that 1, 2, 3, and 4 are actually statistically different from each other. I remember when I was taking that statistics course, it was the number 1500 is stuck in my head. Like for category data, for you to be able to have confidence that 1 is different than 2 in this Likert scale, the 5-option Likert scale from strongly agree, slightly agree, either disagree or agree, disagree or strongly disagree. That's 5 options, and you needed at least like 1,500 surveys to say that 1 was significantly different than 2, or 2 was different than 3, and that's why I have a problem with some of the student evaluations when 7 people, 12 people fill it out. It's not statistically valid at all, and so you can't prove with 7 people that 1 is different than 2, or 2 is different than 3. The value in those evaluations is in the comments, and so I think that I've always been a proponent that if the student isn't invested enough to put a comment, then their bubbles shouldn't count. And I thought that would be at least an interesting study to say, let's run the numbers with all of them, and let's run the numbers of those that made comments and see if they're the same. Anyway, so neither here nor there. What about this control chart? It's drifting for sure. And again, they shouldn't have a slope. And so you're looking at this, and that thing is drifting like this. And so it's not following the trends of the training period. So the green data was the training period, okay? And that's fine, but it's, give it a little bit more time, you start to see that it's drifting. And so here was 1, 2, 3, 4, 5, 6 data points all on one side of the mean. And so we could have probably predicted or detected the drift right here, even before it was really obvious to the eye. So that's the probability of that happening is 0.5 to the 6th power. It doesn't really look like the standard deviation has changed. It's this sort of the same scatter around that data point. So this, I know I just made up this title here, but this is what you see with temperature. So like if this was just temperature, this is what it looks like in the spring, going into spring. It just gets progressively warmer. Okay, and so when we are taking the daily difference, what are we doing? We're taking the derivative of this, and the derivative is constant, so it drops down, and it's got a zero slope. Now, if the data starts to curve, then that daily difference wouldn't work. So we would have a trend in the data with the daily difference. Now, control charting can be automated, so this is nice. Let's say we had an oven that we were supposed to write down the temperature every morning, and you look at it and you're like, look, boss, this takes me X amount of days to write down the temperature, or X amount of minutes to write down the temperature. Over the whole year of 2,000 hours, at my rate, that cost the company $800. Okay, for me to record the temperature with the thermometer and write it in the book and then chart that data. So $800, and we can buy this guy from Granger. Let's say maybe it's 1,000. I want it to be better, right? So it costs $1,000 to the company for me to record this manually. And go to Granger, $960. We'll buy this temperature monitor, and we can put it on our oven, and it'll measure the temperature continuously, and we can come in and see what happened overnight or whatever. And so this is, it's got this nice little chart recorder. You put the paper on there, and you hit go. This one's measuring relative humidity, and maybe something else. It's got two values, so maybe it's temperature and relative humidity, and the numbers go out like this. Okay, and there's days, like, see, this is Friday here. This is 6 a.m. Let's see, Thursday here, 8. Can't read that. 6, maybe that's p.m. And then Friday, Saturday. So it goes around. So it looks like this might be a 1-week disk. And so every week you just pull the disk and put the next disk on, hit go. This is really nice because it can collect data overnight. And you can come in the morning and you can see if you had an excursion. Percent humidity is a really good one if you've got samples that are going to be hygroscopic. They're going to absorb water. And so if you see that your humidity went out of control in this cabinet or whatever, and you've got your potassium hydroxide or something in there that needs to stay dry because you're going to use it to make standards, you now know it's going to be heavier than usual because it's absorbed water. And so you need to not use it or dry it out more. So, here's another one. This is a digital one. So that's kind of nice. It looks the same, right? It plot things on a little disc, but it's a digital disc. And so you just have this record of those things over time. So that's it for today. Any questions left about your control charting thing? Okay, so now you should start putting the chart together. We've talked about it. Get your data in the right format and start making your charts. So I'll be grading on the charts and the data format and everything after this Saturday. Yes?